This is about pH, what it is, why it's important, and how to use it. pH has several sides. There's the chemistry side, which is the subject of pH Part 1. It addresses the question, why should pure water even have a pH? pH wouldn't exist without the unique chemical behavior of water, which we will see is the result of the geometry of the water molecule. Then there's the engineering side, which arises because pH influences so many properties of water, like the solubility and toxicity of substances dissolved in water, corrosion of metals, the transport of nutrients throughout the environment, and the importance of water for all life forms. We start by just dipping a toe into the ocean of pH chemistry. pH. pH is one of the most measured but least understood of all water quality parameters. This is the South Platte River through Denver, Colorado, a valuable water resource for Denver and downstream users. Whenever we want to know how suitable its water is for any particular use, we measure its water quality, measurements that always include pH. But what exactly is pH? Why is it so important? What substance in the water is measured when we measure pH? The most common answers to that last question are hydrogen ion, H+, hydronium ion, H3O+, and I don't know. Of course, you can just call it pH. It doesn't really matter what you call the ion measured by pH meters, but knowing the correct answer can make many properties of pH more understandable. pH Part 1 is a short chemistry lesson about the difference between hydronium and hydrogen ions. Part 2 relates pH with properties of water, like acidity and basicity, and properties of substances in water, like solubility and toxicity. Part 3 will be a series of case histories, showing how pH has been used to understand and sometimes solve real water quality problems. Part 4 offers more details about pH that you don't really need to know, but might find interesting. First of all, because pH depends on the electrical nature of water, we must start with the properties of water at the molecular level. You all know that water has the chemical formula H2O and is formed from 2 hydrogen atoms and 1 oxygen atom. But you might not have wondered why hydrogen and oxygen, like all atoms in the periodic table, are electrically neutral, even though they are composed of electrically charged particles, electrons and protons. Electrons have so little mass and race around so fast they seem like a spherical cloud of negative charge. Protons equal in number to the electrons, but with a positive charge and almost 2,000 times heavier than electrons, are clustered together with neutrons in a tiny nucleus in the center of the electron cloud. Inside the electron cloud, The nucleus and electron cloud are held together as an atom by the attractive force between opposite charges. But outside of the electron cloud, when plus and minus charges are equal, this spherically symmetrical configuration makes plus and minus force fields cancel and makes an atom appear neutral from outside of the electron cloud. But when two neutral hydrogen atoms join one neutral oxygen atom to make a water molecule, electrical charge symmetry is lost. Parts of the electron clouds of all three atoms merge to form chemical bonds, and the hydrogen atoms join the oxygen atom in a bent molecule arrangement. The bent molecule shape destroys the geometric charge symmetry of the neutral atoms. Further loss of charge symmetry occurs because the shared bonding electrons are now exposed to three positive nuclei with different attractive forces. The more highly positive oxygen nucleus with 8 protons attracts the bonding electrons more strongly than do the less positive hydrogen nuclei, 1 proton each. This difference in attractive forces causes the oxygen atom to pull negative charge away from the hydrogen atoms. Movement of negative charge away from the hydrogens toward the more positive oxygen nucleus makes the oxygen end of a water molecule more negative and the hydrogen ends more positive. Water is neutral overall because no electrons are lost or gained when its neutral atoms come together, but every water molecule has electrically charged locations, negative at the oxygen end and positive at the hydrogen ends. And this is because the distribution of electrical charge is no longer symmetrical. Molecules that are electrically neutral overall but have separated plus and minus charged regions are called polar. Water is a polar molecule. In addition to polarity, another property of water important for pH is that water conducts electricity. At the molecular level, this means that water contains ions. The current-carrying ions in most waters are mainly dissolved metal salts that have dissociated into cations, positive, and anions, negative. Municipal and natural waters always conduct electricity because they always contain ions. But before the early 1800s, most chemists believed that pure water would not conduct electricity. They believed that they simply had not been able to remove ions to a low enough concentration to observe zero conductivity. With modern lab techniques, we can test this ion theory. If we purify these waters with membrane filtration, precipitation, and multiple distillations, we can remove these metal salts almost entirely. But as the salt concentration of water is reduced, its electrical conductivity does not approach zero. The electrical conductivity of water approaches a small constant value as the salt concentration approaches zero. This means that even perfectly pure water will conduct a little electricity. The experimental evidence was clear. There must be another source of ions in pure water besides dissolved salts to account for its residual electrical conductivity. It was shown around 1805 that the small conductivity remaining in pure water comes from ions created from water itself. At first, hydrogen ion, H+, and hydroxyl ion, OH-, seemed to be the only possibilities. But this turned out to be wrong. When chemists looked closely at what happens to a hydrogen atom when it becomes a hydrogen ion, they found a problem. As described before, the hydrogen atom consists of two charged units, a negative cloud of just one electron surrounding a positive nucleus consisting of just one proton. A hydrogen ion, H+, is dramatically different from a hydrogen atom, H. It still has the one positive proton, but has lost its only electron by ionization. Without an electron cloud, hydrogen plus, the hydrogen ion, is just a single tiny proton, a positively charged particle. The hydrogen ion has no electron cloud at all. Hydrogen is the only chemical without an electron cloud when it forms a singly charged ion. We saw before that when two hydrogen atoms joined one oxygen atom to make a water molecule, all the chemical action involved changes in the electron clouds. The atoms' clouds merged to make chemical bonds in the water molecule. Chemistry always involves changes in electron clouds. We should not expect hydrogen ion to act like other chemicals because without an electron cloud, it is so different. Because H+ is unshielded by an electron cloud, it is an extremely reactive species. It could exist in a plasma, the high vacuum of outer space, or a particle accelerator. But in water, where pH is measured, H+, the hydrogen ion, disappears immediately after it is made by reacting on its very first collision with a water molecule. How do we know this? The answer involves repulsive forces that exist between the electron clouds of atoms and molecules. Watch two chemical species in water, A and B, approaching each other and heading toward a random thermal collision. They can be atoms, polar species, oppositely charged ions, or molecules. The only requirement is that they both possess a negative electron cloud. Initially, they are far enough apart that the repulsion between their negative electron clouds is negligible compared to their thermokinetic energy. But as they approach one another, their negative electron clouds, 100,000 times larger than their positive nuclei, are the first parts of A and B to electrically interact. As A and B come together, the repulsive force between their negative electron clouds becomes stronger, slowing their approach and pushing their electron clouds away from each other. The repulsive force acts as an energy barrier that tries to prevent the collision. If their thermokinetic energies cannot overcome the repulsive force, A and B just bounce away from each other and continue their random motions. But if the kinetic energies of A and B are strong enough, They can overcome the repulsive force, that is, cross the energy barrier, and press close enough together to allow the positive nuclei of A and B to pull on each other's negative electron cloud and merge into a new molecule, AB. The energy needed to overcome the repulsive force between colliding electron clouds, cross the energy barrier, and merge to become a new molecule is called the reaction activation energy. Because chemical reactions have an activation energy, not every collision results in a reaction, only the most energetic ones. So even if the collision rate is very high, the reaction rate for A and B to merge into the product AB is always much slower. What would happen if there were no electron cloud repulsion? That's the case when the A reactant is H+, a bare proton. In a reaction between a hydrogen ion with no electron cloud and another species with an electron cloud, there is no repulsive force. Therefore, there is no activation energy. There is only an attraction between the positive proton, H+, and the negative electron cloud of B. This attraction gets stronger as the reacting species come together. As H+ gets close to B, the increasing attractive force causes the negative electron cloud around B to stretch out toward the approaching proton. With no energy barrier, the positive proton, H+, is always pulled into the negative electron cloud of B, and the collision partners become the positive ion BH+. Every collision makes a reaction. In liquid water, each molecule is estimated to undergo about 10 to the 12 collisions per second. A hydrogen ion reacting on its first collision with a water molecule would have a lifetime of only a few picoseconds, 10 to the minus 12 seconds, or less. Conductivity in water requires ions to move through the water to an electrode, a process that takes time. Therefore, measuring electrical conductivity requires the presence of persistent ions. It cannot be caused by hydrogen and hydroxyl ions produced in the reaction shown here. The hydrogen ion lifetime is too short. So then, what ions are pH meters really measuring? Let's look at the reaction between two water molecules again. Liquid water is a chaotic assembly of water molecules bouncing about at random because of thermal energy. Because water molecules are polar, colliding molecules tend to orient oxygen minus ends to hydrogen plus ends in each collision. In a collision strong enough to dissociate one water into ions, the hydrogen ion, H+, with no repulsive force, transfers immediately from one water molecule into the negative electron cloud of the other, changing the hydrogen ion receiver into H3O+, a hydronium ion. At the same time, the electron cloud, which originally was around the transferred hydrogen ion, is pulled back into its former water molecule, which becomes OH-, a hydroxyl ion. After the hydrogen ion transfer, the collision partners separate as a hydronium ion H3O+ and a hydroxyl ion OH-. pH meters measure hydronium ions H3O+, not hydrogen ions H+. Now it's time to summarize all of this chemistry. Just 3 properties of water explain why pH meters measure hydronium ions instead of hydrogen ions. First, water is polar. Because water is polar, with plus and minus ends, colliding molecules tend to orient the negative oxygen end of one water close to the positive hydrogen end of the other. Second, pure water conducts electricity. This proves that pure water contains ions. They must be hydrogen ion and hydroxyl ion, formed in collisions energetic enough to dissociate one of the colliding water molecules. And third, the hydrogen ion has no electron cloud. Electron clouds are essential for chemical reactions to have an activation energy. With no electron cloud, hydrogen ion always reacts on its first collision, which, because of water's polarity, is with the oxygen end of the colliding water molecule, where it forms a hydronium ion. With no electron cloud, hydrogen ion disappears almost instantly by reacting with water to make hydronium ion, H3O+. Finally, hydronium ion has an electron cloud and a long enough lifetime to be measured with a pH meter. This ends pH, Part 1 of 4. Part 2 will relate pH to properties of water like acidity and basicity, and properties of substances in water like solubility and toxicity. Stay tuned for parts 2, 3, and 4.